In this video, we're going to do example 3.5.4, where we're going to use the chain rule to find second order partials. So if z is f of xy with no formula given, has continuous second order partials, and x is r squared plus s squared, and y is 2rs, we're asked to find a simplified expression for del squared z del r squared, which is a second order partial in terms of a variable r, in terms of the partials of z because there's no rule given for z. So let us start by making a little tree diagram. We know that our z depends on x and y, and both of those depend on r and s. So we are looking to find the partial with respect to r first, so we're going to go down this way eventually, but let's first write down what we're looking for. We want del squared z del r squared, which, if we remember this notation, is the derivative with respect to r of the first partial of z with respect to r. Now here is where we're going to use the chain rule. The first partial with respect to r we can access through these two branches of the tree diagram. So we can take the partial with respect to r of, and here's the chain rule, del z del x times del x del r plus del z del y times del y del r. Now, we cannot evaluate del z del r because there's no rule given, but del x del r and del y del r we can evaluate. So let's write that del z del r of del z del x and del x del r is 2r, plus del z del y, which has to remain as that expression, times, if we take the derivative of this expression with respect to r, we are going to get 2s. This is the derivative operator, so we have to take the derivative of what's in the bracket here, and the first thing that we can apply is the sum rule. So in fact, I know I'm going to need a little bit more space. I'm going to move all of this over here so that I can have more space on the lines coming down. First thing, the sum rule, so del by del r of the first, which is del z del x times 2r, plus del by del r of the second, which is del z del y times 2s. Now, the next here is going to be, if we deal with the first bracket, both of these depend on r. Not convinced? There's no r in this expression? Well, let's just imagine, for example, what if we had something like z is equal to x cubed y to the fourth, for example. Then del z del x would be 3x squared y to the fourth. And since del z del x has both x's and y's in it, and x's and y depend on r, we would have a tree. Del z del x depends on x and y, and each of those depend on r and s. So even though there's no r apparent, del z del x depends on r. And obviously del z del y by an analogous argument is also going to depend on r. So this has to be a product rule. So I'm going to color code the product rule for us a little bit here. So we're going to have in the first del by del r of del z del x, all of that times 2r, plus the first del z del x times the derivative del by del r of 2r. Next, we've got to apply here. Well, s is not a function of r, So 2s is just a constant. That I can bring out to the front. So plus 2s times del by del r of del z del y. So we've got 3 terms to expand even further. Now, the first here, del by del r of del z del x, that is another chain rule. That's another chain rule. So I've got to use the chain rule on this first product in the term. So let's do that. If I use the chain rule here, I'm going to have del by del, so what do we get here? Del by del r, we know is the same as del by del x times del x del r of something that goes in the bracket, and what goes in the bracket is exactly the same del z del x. Plus, the chain rule has an addition, right? It has to be del by del y times del y del r. And we keep the same del z del x inside, and this also gets multiplied by 2r. Now the term in blue, that's nice. The derivative of 2r with respect to r, well, that's just 2. So I can say that's plus 2 del z del x. And then I have to do the exact same kind of chain rule for del by del r of del z del y. So the 2s I can keep in front, 2s times, and then I apply the chain rule just like I did for the terms in red. So del by del r is the same thing as del by del x times del x del r, keeping the same del z del y, plus del by del y times del y del r, keeping the same del z by del y. Now we can clean this up a little bit. This first term here, that notation is exactly what we would have written as del squared z del x squared times, and we know del x del r is 2r, so times 2r times 2r, which is already there. This derivative we can write as del squared z del y del x. Del y del r is something that we can evaluate again. That's 2s. So this is going to be times 2s times 2r. We can just recopy the 2 del z del x. And then we can go and multiply through our 2s's into each term while cleaning these up. So we are going to have plus del squared z del x del y times 2s times, and this we can evaluate again, del x del r is 2r, plus del squared z del y squared times the 2s that we've multiplied in times del y del r is again 2s. So writing this all cleaned up, we would have 4r squared del squared z del x squared plus 4 SR del squared z del y del z plus 2 del z del x plus 4 SR del squared z del x del y, and lastly plus 4 s squared del squared z del y squared. And we would ordinarily be done, except we were asked to simplify as much as possible, and we were told that Z has continuous second order partials. That gives us some information about these mixed partials. It tells us that they are equal. They are equal because of Clairaut's theorem. So that means I can combine those two together and give a final answer of 4r squared del squared z del x squared, plus if we combine these together, 8sr del squared z, doesn't matter if I write del y del x or del x del y, plus 2 del z del r plus 4 s squared del squared z del y squared.